Hello, so picking up from where we left off last time, we were just looking at how to take the antiderivative of some functions. So we've seen how to take the antiderivative of powers of x, and using what we know about what happens when we take derivatives with constants in them, we will see how to take antiderivatives of functions with constants in them. So if I take the derivative of something with a constant out front, we can just pull that constant out. And it turns out that if we can do this for derivatives, this definitely means that we can do this also for antiderivatives. So we can pull a constant out of an antiderivative. So if I'm taking a times a function, if I'm taking the antiderivative of a times a function, it's just going to be a times the antiderivative of that function. So we can look at a few examples here. So I have 2 times x squared. So first and foremost, I've got this 2 out front. I can pull the 2 outside of the antiderivative. And then from here, it's just using our power rule. So again, the way that the power rule works for antiderivatives, we raise it to the 1 bigger power, and then we divide it by that power. So this is going to be, again, x to the 3rd power, and then we need to divide it by 3. And then if I simplify this, 2 times a 3rd is 2/3 times x to the 3rd power. Cool. So there's our antiderivative. And we've got 7 over x to the 4th, which I can rewrite this as I can pull the 7 out, and I can take the antiderivative of 1 over x to the 4th. But 1 over x to the 4th, that's the same thing as x to the minus 4th. So I'm just rewriting 1 over x to the 4th as x to the minus 4th. And then I do the same thing. I go through the same process. I have pulled the 7 out, so the 7 is just going to hang around. And then I'll take x, raise it to the 1 higher power, and I divide by that power. And then, so everyone should be yelling at the screen right now because I forgot my plus c on my previous problem. So plus c, every antiderivative will have that plus c because when I take the derivative and I try to go backwards, the derivative of that is just 0, so I do get my original function back no matter what that c is. So I can't forget my plus c. You should be yelling at me right now. So here I've got 7 over negative 3, so that's negative 7/3 times x to the negative 3 power, but x to the negative 3 is the same thing as 1 over x to the 3rd power. My 3's are getting a bit sloppy, plus c. So there is my antiderivative. So here, when I see the antiderivative of 17, this may look a little bit silly. I'm going to go through all the steps, but you don't necessarily have to do all this for the integral of a constant function. I'm going to pull a 17 out, and what's left in here is just 1. So if you pull a 17 out of a 17, you're just left with a multiple of 1, which 1 is the same thing as x to the 0 power, which when I take the antiderivative of x to the 0 power, I raise it to the 1 higher power, I divide it by that power, and I can't forget my plus c's. It's always got to be there. And then 1 divided by 1 is just 1 times anything is just 1. So this is going to be 17. X to the 1st power is just x plus c. So the integral of a constant we can kind of see is just going to be that constant times x. So it's pretty easy to just skip from the first line to the last line. The integral of a constant by itself is just going to be that constant times x plus c. Can't forget that plus c like I just did. And then down here we've got 3x to the 1/2, so I can pull out the 3, and then I'm taking the antiderivative of x to the 1/2, it's the square root of x, and here again, this works just like normal. I'll raise it to the 1 higher power. 1 more than 1/2 is 3/2, and then I will divide it by 3/2, and then I have my plus c. So 1 divided by 3/2 is 2/3. And then if I simplify this, 3 times 2/3, that's just 2x to the 3/2 plus c. So there is my antiderivative. So we've seen how to take antiderivatives of x to a power. What happens if we have an extra constant in there? We can just pull those constants out. The next step is looking at the sum and differences. So for derivatives, this was pretty easy. The derivative of f plus g or f minus g is just, we take the derivative of each one and then we add them together or subtract them, as the case might be. The rule for antiderivatives is exactly the same. If I'm taking the antiderivative of f plus g, this is going to be the antiderivative of f plus the antiderivative of g. And the same thing if it were subtracting. If it were subtraction, I would just have subtraction. So we'll just do plus or minus is plus or minus, and you use the appropriate one. It's just the same one. So let's go through a few examples here. We've got the integral of the antiderivative of 2 plus x dx is just going to be the antiderivative of 2 plus the antiderivative of x. And then the antiderivative of 2, like we just had said before, this is going to be 2x. The antiderivative of x is going to be x to the 1 higher power. So 1 more than 2 is going to be, 1 more than 1 is 2, and then I have to divide by 2. And I can't forget my plus c at the end. Now, just as a little aside, you might think, okay, so I have one derivative here, so I have one constant at the end. Here I have 2 derivatives. So should this actually be 2x plus c plus 1/2 x squared plus c? Well, the thing is, we don't know what those constants are meant to be. And if there's 2 constants here, and we add 2 unknowns together, what do we get? Well, we don't know. So I could write a plus c and a plus c, but what is c? We don't know. It's just any number. So why don't we just write plus c once? Because c plus c is going to be another unknown. We could say, okay, maybe if I have plus c, maybe I call c plus c d, because I don't know what that number is. And I could write this whole thing plus d at the end. Essentially, the short version is that we will always have a constant at the end of an antiderivative. So even if we have multiple constants, constants plus constants is just another constant. So we'll just write plus c here at the end. The next one, we've got a minus sign in here. So this is going to be the antiderivative of 3x squared dx minus antiderivative of 4x to the 5th dx. And again, I'm taking the antiderivative of a single function, so I know that I'll end up with a plus c at the end. So I don't have to worry about, say, a constant coming from this antiderivative and this antiderivative. I'll just have 1 at the end for this guy. And then I have 3 x squared. When I take the antiderivative, I raise it to the 1 higher power, and I divide it by that power. And I'm going to subtract 4 times, okay, so x to the 5th becomes x to the 6th, and I need to divide by that power. So simplifying, 3 times a third is just 1, so this just becomes x cubed minus 4 divided by 6, well, that's 2/3 times x to the 6th plus c. Again, all of our antiderivatives we'll have a plus c at the end. And then let's do one more. So here I've got x to the 1/2 minus x to the minus 1/2. So again, I can just take the antiderivative of both of these individually. I don't even have any constants in here, so I don't need to worry about that. I can just take x, I raise it to the 1 higher power, so 1 more than 1/2 is 3/2, and I divide it by 3/2, that power there. And subtract, okay, so I'll take x, I need to raise it 1 higher power. 1 more than -1/2 is +1/2, and then I divide it by that power, and then I add c. Can't forget c. 1 divided by 3/2 is just 2/3. Minus 1 divided by 1/2 is 2. Plus c. So far, so good. We've seen how to take antiderivatives of x to powers, functions with constants in them. We can pull constants out, and then now we've sort of added and subtracted functions from one another. The next thing is to look at derivatives and derivatives and antiderivatives of exponential functions. And I have an asterisk here next to exponentials. These are a very specific type of exponentials. So we're not really going to worry about finding the antiderivative of any number to the x power. We're really going to focus on e to a power here. And more than that, we're only going to take e and we're going to raise it to a constant times x. So this is really just a very, very specific case for exponentials, and we will deal with harder, more complex exponential functions in the future. But for the moment, the derivative of e to a power is always just going to be e to that power. This is one of the very nice things about derivatives of exponential functions, base e. But we need to take it times the derivative of what's upstairs. Well, the derivative of a times x is just a. So this is going to be a e to the ax. So simplifying this, the derivative of e to the ax is e to the ax times a. Well, for the antiderivative, we need to do the opposite of this. So if I take the antiderivative of e to the ax, it's going to be e to the ax divided by a rather than multiplying by a. So this is the inverse function in there, and I can't forget my c. So this is all there is to exponentials. So let's take a few antiderivatives. The antiderivative of e to the 2x. Again, almost everything stays the same. I still have the e to the 2x, but I'm going to divide by 2. And I can't forget my c. So derivatives of exponentials are very easy. Antiderivatives of exponentials are very easy. We will see that once the exponentials become more complex, they get pretty hard. But for the moment, this is all there really is to it. And then the antiderivative of e to the x, again, is going to be e to the x divided by 1, because this is 1 times x. But what is 1 divided by 1? That's just e to the x. And this makes sense, because we know that the derivative of e to the x is e to the x. So the antiderivative of e to the x should be e to the x plus c. You can't forget the plus c. But exponentials are quite nice. And then the same rules sort of apply for adding and subtracting functions as well. This is going to be the antiderivative of 12x to the 5th minus dx minus the antiderivative of e to the 1/3 x dx. This first one, I can pull out the 12, and then I'll just take it times the antiderivative of x to the 5th, which is going to be x to the 6th divided by 6, minus, well, this is e to the 1/3 x divided by 1/3. And I can't forget the plus c. And simplifying, 12 divided by 6 is 2. 1 divided by a third is 3.